Okay, so we're going to move on and start trigonometry, but I want to see what you guys remember from grade 10. So in grade 10, you looked at solving right triangles using the primary trigonometric ratios, and you looked at solving acute triangles using sine law and cosine law. For now, I want to focus on the right angle triangles. So in a right angle triangle, one thing you remember from grade 10 is there's three primary trigonometric ratios. So again, just to remind yourself here, let's say you have a right triangle here. Let's say you have an angle that we're going to call theta. Now, to label these three sides, all these sides have names. The longest side, the one across from the right angle, was called the hypotenuse. The side across from the angle that you're indicated here, in this case theta, is going to be the opposite side. So go across the triangle from theta, you get the opposite side, and the one left over is going to be the adjacent side, the one that moves along the angle. So we had three primary trigonometric ratios: sine, cosine, and tangent. And sine theta was the ratio between opposite and the hypotenuse. Cosine theta was the ratio between adjacent and hypotenuse. And then tan theta was the ratio between opposite and adjacent. Okay, so those are the three ratios that you worked on last year. So as long as you knew an angle and a side, you could solve for any other side inside the triangle. If you knew two sides, you could solve for any angle you wanted inside the triangle. So that's what we used it for last year in grade 10. We're just going to review that a little bit before we move on. And one thing to remember with your calculators, make sure they are in degree mode. Sometimes they get accidentally switched over to radian mode or gradient mode, and none of your answers will be correct. So just make sure they're in degree mode. Okay, so what I'd like you to do now is, given the triangle below, I just want you to just practice writing out the trigonometric ratios. So I'm giving you the triangle WLK. I want you to write out the ratios: sine W, cosine W, and tan W, sine K, cosine K, and tan K. And again, just express it in terms of the variables we have for the sides over there. So give that a try. When you're finished, push play and we'll go through it together, and we'll discuss some patterns we might see in these trig ratios. Okay, so take a second here and check your answers. So again, these ratios are expressed in terms of the variables we use for those three sides in the triangle. Here's a couple things I want you to notice here. And you may remember some of this from last year, but you might not. One thing you might notice here is that the sine of W is equal to the cosine of K. Okay, and the opposite is also true. The cosine of W is equal to the sine of K. Okay, so that's one thing that we can notice looking at the ratios in this triangle. And if you think about it, that kind of actually makes sense. Because if you think about it here, remember, sine is opposite over adjacent. The opposite side to angle W is side W, but that's also the adjacent side to side K. So, the adjacent side to angle K. So that means that, again, the ratio for sine of W and the ratio for cosine of K use the exact same sides. So this relationship will always be true as long as W and K are angles in a right triangle, i.e. they're complementary. So meaning that they add up to 90 degrees. So for example, if you have the sine of 70 degrees, that will always be true, always be equal to the cosine of 20 degrees. And you can check that in your calculator just to be sure, but this will be true for any pair of angles that add up to 90 degrees. The sine of one angle will be equal to the cosine of the other angle. Okay, one other thing that you may notice here, just by looking at the relationship between the tan of one angle and the tan of the other, they are reciprocals of each other. So that's another relationship that you may notice. And also, this one might not be as easy to see, but tan is equal to sine over cosine. So tan W is equal to sine W over cosine W. Tan K is equal to sine K over cosine K. Just to prove to you that that's actually the case, if I look at tan W here, I know that's equal to W over K. So that's given right here. I figured that out. Now, if I do sine W over cosine W, that's going to give me W over L all over K over L. Okay, so again, this is going to be sine W over cosine W. So you might be able to see right away that the L's here are going to cancel out, but in case you don't, what I'm going to do is write this division in a more traditional way for writing out division of fractions. So W over L divided by K over L. I haven't actually changed anything here, just rewriting the division in a different way. And you do remember, of course, from multiplying and dividing fractions, that when you divide fractions, you're multiplying by the reciprocal. So this is going to be multiplied by L over K. So now you can see very, very clearly that the L's are going to cancel, and you're going to be left with W over K, which is the same thing as tan W. Okay, and that's going to be true for any angle. The tan of an angle is going to be equal to the sine of that angle divided by the cosine of that same angle. Okay, so what I'd like you guys to do now, there are three triangles right here. I want you to try and apply SOHCAHTOA, everything you learned back in grade 10, to try and solve for the unknown amounts here. So in this first one, you're going to solve for the angle, and in B and C, you're going to solve for this unknown side indicated by X. So give those a try first, see what you remember. Work together with someone if it helps, And when you've got them all done, push play, and we'll go through them together to make sure you're on the right track for grade 11. Alright, so take a second here and check your answers. So you should get 51.5 degrees for the angle in A, 5.6 for the length of x in B, and 6.3 for the length of x in C. If you got all these answers correct, you can go ahead and move on to the next examples or to the next slide. But if you're not sure where these came from, just you can walk through them here with me. So first thing I always do when I'm dealing with a right triangle is label the sides of the triangle. So for example, in this case, if theta is the angle I'm working with here, then 5.6 will be the side adjacent to it, and 9 will be the hypotenuse. So remember, when you're trying to choose a trigonometric ratio, sine, cosine, or tan, you always want to make sure that you know two of the three unknowns in each ratio. Remember, each ratio has an angle and two sides in it. So you know two of the three, and that the missing variable, the missing unknown, is what you're looking for. So if you're looking for the angle here, the angle will be unknown, so you better know both sides. So which ratio has both adjacent and hypotenuse in it? It's going to be cosine. So you set it up, cosine theta is going to be equal to 5.6 divided by 9. And then all we need to do now is isolate for theta. So how do we isolate for theta here? How do we get theta by itself? Remember the operation we used last year when you're solving for an angle? It's going to be the inverse cosine. So again, what that tells you is you know that the ratio between the adjacent and the hypotenuse is going to be 5.6 over 9. The cosine inverse function will give you the angle that gives that ratio. So you do on your calculator cosine inverse of 5.6 divided by 9, and you get 51.5 degrees for an angle. Okay, in part B, the unknown is a side length. So using the given angle of 34 degrees, I know that the side across from it, x, is going to be the opposite, and 10 is the hypotenuse. So if my unknown is the opposite side, I want to choose a ratio that has the opposite in it so I can solve for it. I have the hypotenuse and the angle, so which ratio has both opposite and hypotenuse is going to be the sine ratio. So sine of 34 degrees is going to be equal to my opposite, which is x, over my hypotenuse, which is 10. And then from here on in, it is just algebra. So I'm going to multiply both sides of the equation by 10 to isolate for x. So I wind up with 10 times the sine of 34 degrees, which when I run through my calculator, it gives me 5.6. Okay, and last but not least, with this last triangle here, with a given angle of 52 degrees, I have the opposite side. I'm looking for the adjacent side. So the ratio that involves both opposite and adjacent is the tan ratio. So the tan of 52 degrees is equal to 8, my opposite, divided by x, my adjacent. And once again, once the setup is just algebra. The algebra is a little bit tricky here because your unknown is in the denominator. So there's a lot of algebra mistakes that can very easily happen here if you're not careful. What you want to do is get the x out of the denominator by multiplying both sides by x. So you wind up with x times the tan of 52. Remember, tan of 52 is just a number. That's going to be equal to 8. And then how do you solve for x? Well, again, tan of 52 is just a number, so you can divide both sides of the equation by the tan of 52 degrees. Okay, that gives you 8 divided by tan 52. When you run that through your calculator, you get 6.3 for a length. Okay, so that's a quick and dirty review of grade 10 right angle trigonometry. What I want to do is take it a little bit further now and take a look at some special triangles here. So right now, down below, I have two triangles. One's an isosceles right triangle with the two same sides being length 1, and one is an equilateral triangle with all side lengths of 2. What I'd like you to do is, using these triangles below, I want you to complete this chart. So find the sine, cosine, and tangent of 30 degrees, 45 degrees, and 60 degrees. Okay, so before you do this, you should solve for some information in these triangles that's not necessarily given to you. So one thing you know, if this is an isosceles triangle and one of the angles is 90 degrees, these two angles here should be the same. So I have 90 degrees left in the triangle to divide over these two angles. So that's going to tell me I should have a 45 degree angle in both this corner and in this corner. Okay. Also, if it's an equilateral triangle, that means all three angles should be the same. So every angle inside the triangle should be 60 degrees. Okay, to take it a step further, you know Pythagorean theorem, so you should be able to solve for this hypotenuse here in this right triangle. So remember, x squared, or a squared plus b squared equals c squared. So that should tell me in this situation that 1 squared plus 1 squared, if I call this x, will be equal to x squared. So 1 squared plus 1 squared is 2. So x is going to be equal to the square root of 2. Okay, so that's going to give me this side length right here. And I should have everything I need here to find all the ratios for 45 degrees, sine, cosine, and tangent. Okay, I'm going to let you try that on your own in a second, but now let's take a look at this other triangle over here. What I'm going to do over here to generate the 30 degree angle, you can see I have a 60 degree angle, but what I want is a right triangle in here. So I'm going to drop this height down right here to split this up into two triangles. So if I do that, the 60-degree angle at the top has been cut in half, so I have a 30-degree angle up here. Okay, I have a right triangle down here. And what I need to do is now figure out the side lengths for all my missing sides. So along the bottom here, again, the whole thing has a side length of 2, so if it's been cut in half, this little piece has a length of 1. And I should be able to solve for this missing side if I call that, let's say, C. Well, maybe not C. Let's call that D instead. So I can solve for D, again, using Pythagorean theorem. So again, D squared plus 1 squared should be the hypotenuse squared. The hypotenuse is 2, so I get 2 squared. So I get D squared plus 1 equals 4. So D squared equals 3. So D is equal to the square root of 3. So now what I actually have inside this triangle is all three lengths and all the angles again. So now, with these two special triangles, again, one is an isosceles triangle with 45-degree angles in it, one was an equilateral triangle with side lengths of 2 that I dropped a height down to cut in half. I now have angles of 30 degrees, 60 degrees in this right triangle, and an angle of 45 degrees in this right triangle. I should be able to solve for all of the ratios for sine, cosine, and tangent of 30 degrees, 45 degrees, and 60 degrees without too much trouble. So I'm going to have you guys do that on your own. Take a couple minutes, fill in the chart, we'll check them together, and then we'll talk about what's important about these values. Okay, so there's your chart filled in. Just to remind ourselves where a couple of these came from, let's deal with the 30-degree angle case for a second. So a 30-degree angle, let's say I want the sine of 30 degrees. So from 30 degrees, sine is opposite over hypotenuse. So the opposite side is 1, the hypotenuse is 2, so sine of 30 degrees is 1 over 2. For cosine of root 3 over 2, for cosine of 30 degrees, it's going to be cosine of 30 is adjacent, which is root 3 over hypotenuse, which is 2, which is why I get root 3 over 2. And tan will be opposite over adjacent, which is how I get 1 over root 3. So this continues similarly for the 45-degree and 60-degree angles. So these are special angles that come from these triangles. These are going to be key values that are going to come up a lot in trigonometry, not both this year and next year. So you need to be able to know these exact values. Now, some of you can see in your calculator, right? I mean, if you do sine of 30 in your calculator, it's going to tell you it's 0.5. If you do tan of 45, it's going to tell you it's 1. But if you try any of the other ones in your calculator, it's going to give you a decimal. But you need to be able to find them out exactly. So instead of memorizing the table, I don't think memorizing the table is a very good idea. Just remember these true triangles. Okay, so remember that if from an isosceles triangle with 45-degree angles, you have side lengths of 1 and 1, you can get a hypotenuse of root 2. You can generate all of these three ratios right here. Okay, for the case of a 30-degree, 60-degree, 90-degree triangle, you have side lengths of 1, 2, and root 3. And if you're ever confused as to where they go, remember the smallest angle goes across from the smallest side. So the smallest side is 1, goes across the smallest angle, which is 30 degrees. The largest side between 2 and root 3, well, 2 is actually larger than root 3, so that goes across from the 90-degree angle, and then you have root 3 across from the 60. If you memorize these two triangles, then you should be able to generate all these ratios whenever you need them, and you'll never have to memorize this entire table. Okay, so also, in addition to what you learned in grade 10, so in grade 10 you looked at the three primary trigonometric ratios, which were again sine, cosine, and tangent. There exist also three other trigonometric ratios which are called the reciprocal ratios. They're called the reciprocal ratios because they are reciprocals of the ones you've already seen. So for example, one new ratio is called the cosecant ratio, and cosecant is a reciprocal of sine. So it's going to be 1 over sine theta, and since sine theta is opposite over hypotenuse, cosecant theta will be hypotenuse divided by opposite. Okay, now we also have the secant ratio, which is abbreviated by SEC. So that's going to be 1 over cosine, so it's going to be a reciprocal of cosine, so it's going to be the hypotenuse divided by the adjacent side. And last but not least, you have the cotangent, which of course will then be the reciprocal of the tan ratio, so you have adjacent over opposite. Okay, now these are three other ratios, three other trigonometric ratios. These are not buttons on your calculator. So if you're trying to evaluate a cotan, secant, or cosecant ratio, you're going to have to probably express it in terms of the ratios that we know and love from grade 10, sine, cosine, and tangent, before we evaluate them. Okay, just something to keep in mind as we move forward. Okay, so that's a good place to pause this for now. We're just going to finish this up in part 2 of the lesson, and we'll finish this up over there. Okay, see you over there.